All right. Good afternoon, everyone. Welcome to the makeup session of the AP Stats Cram finale. We're going to be live here from 4 p.m. to about 5 p.m.-ish Eastern. I see there are some folks here, so please be sure to, I've opened the chat so you can use that feature. It was closed during the main 5-hour finale, but you should see a few things on your screen. Okay, so you should see, the Fiveable logo, myself. There's a big green button that should say AP Stats Cram Hub. Just be aware that forum, the Q&A forum, is not going to be active during this particular session. But I wanted to have that hub there as the resources for other slides and the 5-hour replay from before. So use the chat for questions during this next hour or so. Welcome. I did want to ask before we get started, if you're willing to share, just like kind of what's leading you to the makeup session. So did you have an issue with submitting the first time? Did you just decide to wait to take the exam, or kind of like what brings you here, just so I know what we're kind of working with. And then, like I said, at the bottom there's that green button where you can access lots of resources, because we're not going to do a ton of content today. My goal is to really just kind of highlight some free response practice problems and practice answers, so that you guys get a sense of the kinds of questions being asked on this year's AP Stats exam. Welcome to those of you who are here. Hello to those of you that said hey in the chat, and let's get into it. So big picture wise, AP Stats, you guys know there are 9 units of content, but okay, units 8 and 9 are not covered on the AP Stats exam. So only 1 through 7 is fair game. You guys have 2 questions tomorrow. The first one is timed for 30 minutes. They recommend you take 25 so that you can spend the last 5 minutes uploading. That question is likely, I can't guarantee, but it is likely going to have 6 parts, an A through F. And then the second question is going to be question 2 will be about 15 to 20 minutes. You'll have a full 20 minutes. But you'll have to upload after about 15 minutes or so. That will probably have 5 parts. Buzz I'm hearing from students for the most part is question 1, you're usually able to get through everything. Question 2 might be a little dicey. Don't stress. Don't stress about if you can't finish a single part. And I'm seeing some folks are, some people were out of town the initial exam, or just, couldn't submit the first time around. And hey, welcome. You bought yourself a little bit of extra time, and definitely, especially after this first hour, if there's something that comes up where you're not sure about content, definitely use the resources from the first cram session. So I will say that I am not intending for this to be a let's learn all the content of the course session. This is intended to be a let's hit some highlights and let's do some practice questions. So I hope you guys are active in the chat today, because I'll definitely have some problems for you to practice. Because what I wanted to do is spend maybe 10 or 15 minutes doing some quick hits from each unit. Things that I noticed, things that have been coming up, things that I want to emphasize maybe a little differently than what we emphasized on the initial 5-hour stream. And then we're actually going to get into the practice problems. So let's do that. Okay, so unit 1 is all about describing and comparing distributions. So that's where you first learned about categorical variables, quantitative variables, and if you were a student in my class and you were asked to, describe a distribution or write a few sentences to describe something, you would think of the acronym CUS. Angela, I see your question. Yes, the tests, like the inference test, that's unit 6 and 7. So we're definitely going to be covering those different procedures. Okay, I want to spend kind of 10 minutes-ish, like lecturing, so to speak, about just some of the main things I wanted to remind people of, and then we're actually getting into practice questions. The end will also have some Q&A of just like, we can try to go through a couple individual topics. But if you've never seen this acronym before, CUSS, it's to remind you that you need to talk about a measure of center. So if you're looking at this stem plot on the right side, you have all the numbers available to you. You could find the mean, or you could find the median. Typically, median's usually good to talk about because it's universal to lots of different data sets. You have to talk about any unusual features. Unusual features means you have to mention if there are any clear outliers. You don't have to show a procedure for determining outliers unless you're explicitly asked to do so. If you are asked if anything is unusual, or would it be unusual to see a specific thing? Like, is the crow with 3.0 unusual? Or is the crow with 6.8, the scenario I think was about crows, unusual? Okay, there's two methods you can use. Okay, you can either use the interquartile range, multiply it by 1.5, and then use that from the boundaries of Q1 and Q3, subtract it from Q1, add it to Q3, and that gives you boundary points to determine if they're outliers. Or any individual that is outside of 2 standard deviations of the mean is widely accepted as an unusual observation. Okay, and if there are any gaps in data, you should mention that. You have to describe a shape. Okay, when describing shape, remember that the word approximately is your friend. Okay, this distribution that I'm looking at, I would call it approximately or roughly symmetric. Okay, if you really want to call it approximately normal, you maybe can, but it is slightly skewed to the left. Either of those would be okay. Just the word unimodal is not enough. If you're looking at this and saying, oh, it's unimodal, the peak's around 5, you'd have to say unimodal and approximately symmetric, or unimodal and approximate, roughly skewed left. Okay, bimodal will be okay. Range, interquartile range, standard deviation are all measures of spread. And then we include context by mentioning the variable and referencing units. That's if you have to describe a distribution. If you have to compare distributions where you're given multiple graphs, remember the biggest thing is that you need to use comparison statements. So that doesn't mean just say the median salary at Corporation A is this, the median salary at Corporation B is that. You need to make a clear, explicit comparison between them. The median salary at Corporation A is greater than, is less than, or is about the same as the median salary at Corporation B. In this case, looking at those box plots, I would say that the median salary at Corporation A is roughly the same as the median salary at Corporation B. And I would say that either the range or the interquartile range, whatever measure of spread you want to use at Corporation A, is larger than the range or interquartile range of salaries at Corporation B. And then notice those stars indicate outliers on Corporation A. So I'd have to mention Corporation A has some individuals who make very high salaries, while Corporation B does not. So if you're describing data from one graph, you should give your estimates of whatever measures of center and spread you're using. But if you're comparing data on multiple graphs, all you got to do is make comparisons. You don't actually have to give the numbers. Okay, numbers are nice, but you don't need to. The biggest thing is remember not just to list stuff. So in Unit 1, I mean, describing and comparing data is pretty much everything there is. If you want to learn more about like how does the mean and median get affected by outliers, what does skew do to those things, I'm gonna point you to the resources at the bottom of the page. Okay, I'm gonna skip Unit 2. So if we look at the big picture, okay, Unit 2 is like 5-ish% of the exam, and while I haven't seen all the questions that were given last time, and I can't really comment on the ones that I have, Unit 2 doesn't seem to be showing up very much. That's like linear regression and scatter plots and that kind of thing. We're not really seeing much of that, but what we are seeing a lot of is Unit 3, which is about surveys, observational studies, and experiments. So take a second here, look at the list on the right, okay? And I'm curious, just all those vocab terms, are there any of those vocab terms that you watching feel uncomfortable with? Uncomfortable with either defining or describing? So there's, I think, 9 terms there. Are there any of them that you feel uncomfortable looking at? If so, I'll talk about them for a second here. So experimental units, treatments, response variable, control group, placebo, comparison, random assignment, replication, blinding. If I don't see any words pop up in the chat in like, yeah, okay, confounding variables. You're right, I didn't put the word confounding down there. Okay, blinding, okay, cool. Random assignment sampling. Zane, you are one step ahead of me. That's actually my next slide. Jeffrey, simulations wouldn't come up in experiment vocabulary. So, all right, here's a scenario, okay? The chemical company developed new fertilizer, designs an experiment to test its effectiveness. 30 equally sized plots of land, 20 tomato plants are planted. So picture 30 little squares, and on each square there's 20 plants. The plots are randomly split into 3 groups. One group receives 2 pounds of fertilizer per day, second receives 1 pound of fertilizer per day, and the third receives no fertilizer. Plots are given the same amount of water and sunlight throughout. And at the end of 2 months, the mean weight of the tomatoes in each plot is measured, okay, or average weight. So the response variable here is weight of tomatoes, or mean weight of tomatoes in the plot. Okay. Experimental units is a fancy way of describing what is receiving the treatments. In this case, you can see the treatments are the different types of fertilizer, or different amounts of fertilizer, 2 pounds, 1 pound, or no pounds. So the experimental units are not tomato plants. The experimental units are the plots of land, or the groups of 20 tomato plants, because you're not giving each plant a certain amount of fertilizer. You're giving each plot of plants a certain amount of fertilizer. Okay, so this is like, another example would be like fish in a tank versus the tank itself. If you're assigning a specific type of food to the whole tank, then the experimental unit is not an individual fish. It is the fish in that tank. Okay, when you're doing experiments with people, most of the time, individual people are experimental units. But if there's an experiment that doesn't involve people, look out for there being groups of things receiving treatments and not just like individual. If it's about cats or dogs, it's probably going to be an individual cat or dog. The treatments in this case are the different amounts of fertilizer. Response variable is the average weight. Control group, there is a control group because there is a group that gets no fertilizer. There's no placebo in this case because it's not like you gave them fake fertilizer, just gave them nothing. Okay, placebos are typically used in experiments with humans, where someone will be given a treatment that contains active medication or active ingredient, and the other treatment is designed to look like it, but not contain the active ingredient. So perhaps you're trying to test a new skin cream that has some medication in it. A placebo group would get a skin cream that doesn't have the medication in it, but they would be applying it just like the group that has it. And the reason we do all that is to compare the treatments, to try to make sure that things are fair when we're comparing the treatments at the end. Random assignment happens, we'll talk about in a second. Replication is the idea of having multiple experimental units getting each treatment. So in this case, the fact that there are 10 plots getting each of the different types of fertilizers is going to ensure replication. Blinding means you don't know what type of treatment you're receiving. So blinding only happens with human trials. So back to the thing with the medication. If I'm in that experiment with the skin cream, okay, and I don't know if my cream has medication in it or not, then I am blind to that treatment. And if the study is double blind, that also means that the person who's going to evaluate my skin at the end, who's going to look at it to determine, have I, whatever the goal of the situation was, they won't know if I got the medication or the placebo either. And the reason we double blind is to reduce the possibility of experimenter bias, that we might, act a certain way because we know the situation. Okay. Someone just asked about random assignment versus random selection. Okay. So in unit 3, we talk about like how to take different types of samples. So there's stratified samples, cluster samples, simple random samples, but you also deal with random assignment when it comes to experiments. Okay. The key distinction between random selection and random assignment is that random selection is the thing that lets you take the results of your survey, the results of your observational study, or the results of your experiment, and generalize those results to a larger population. Okay, so if you randomly select 100 people who have a certain illness and tell them to take a certain medication, and then observe how many of them get cured, you can then generalize the results of that observational study to the population of all people who have that particular illness that you were testing. If you recruit volunteers for something, then whatever study you did, whether it's a survey or an experiment, the results can only live with those individuals. Whereas if you do an experiment that has random assignment of individuals to separate treatments, that allows you to assume that the results you get in the end of the experiment could be traced back to causation between the two treatments. So in the case of the tomato plants thing that we just did, if the group that gets more fertilizer ends up growing more, okay, well, We made sure there were the same number of plants in each plot. We made sure they all got the same sunlight. We made sure they all got the same water. The only thing that was randomly assigned was how much fertilizer you get. So now we can say, oh, the fertilizer causes the difference. Okay. If you're dealing with a scenario with an experiment, having volunteers isn't necessarily a bad thing. If you're dealing with a scenario that deals with a survey, volunteers is probably a bad thing. The results of that survey will probably be biased. If you're doing an observational study or you're doing a survey, random selection is imperative to be able to do any kind of inference procedure or generalize your results at all. If you're doing an experiment, if you do random selection before you do random assignment, you can not only assume that the treatments cause whatever differences you observe, but also those results would apply to a larger group of individuals. Okay, Aisha, the different types of sampling strategies, I might touch on them a little bit later. I'm actually going to point you to the resources below. Probably in about hour 1 or hour 2 of the first stream, Bob did a good job of going through the different types of sample designs. And I'll link you to a couple of resources later if they come up. I do want to keep moving because I said this would be 10 or 15 minutes, and I'm coming up towards the end of that. Okay, in Unit 4, okay, a big thing that I've been noticing people might need a refresher on is independent events. Okay, if an experiment has volunteers that are randomly assigned, then if there are statistically significant results, you can attribute those results to the treatments. So you can say, like, the medication caused the people in the experiment to have a reduced whatever or a greater whatever. But you can't necessarily say that that will apply to the entire population of individuals that are unlike the ones that were in the experiment because the people weren't randomly selected. That's going to be the key distinction. And we're going to see a sample problem like that in a few minutes here. Okay. If you get a two-way table like this, okay, remember that independent events are based on this definition. Okay. So that first symbol PA/B, that stands for the conditional probability of A given B. In other words, Vikrant, possibly. A given B equals the probability of A. So what that one is saying, like, hey, get the probability of a general thing. So in this table, for example, the probability of out of the 500 people picking an athlete, or out of the 500 people picking someone with a GPA of less than 2.5. Okay, if I just pick one of those overall things and calculate that probability, if I then calculate a conditional probability restricted to a specific row or specific column, if those two things match, the events are independent, and if they don't, not independent. So in the case of, let's say, athlete and low GPA, okay, in this very specific example, okay, 190 out of 500 people are athletes. So the probability that I randomly select an athlete is 38%. But if I restrict myself to athletes out of all the people with low GPAs, so now I say, hey, what's the probability that you get an athlete given that the person has a low GPA, given this additional piece of information? Okay, well, now I'm restricted to 40 people out of 95. So that 0.42 came from 40 out of 95. That's 42%. So the general population of athletes in this particular group is 38%. But out of the people with low GPAs, 42% are athletes. So if I know someone has a low GPA, in this case, they're more likely to be an athlete. So those two events are not independent. Yes, they would have to be exactly the same for us to declare independence in a case like this. Okay. The other thing that's been coming up is the idea of if something is or is not binomial. So when you do like multiple trials of something, okay, or you do random samples, a lot of times something can qualify as being a binomial random variable or not. Okay, remember the conditions for binomial random variables, it's BIN. You have to prove that something is binary. In other words, every trial either ends in success or failure. Okay, success will typically be defined for you. So like, we're going to select 10 people from this population, and we're going to count the number of athletes in our sample. So every person you pick is either an athlete or not. So success or failure. Okay, independent. The trials must be independent, meaning that the result of one has nothing to do with the other, like we just saw. So if you know something's already happened, the next trial cannot be dependent on the previous trial. Okay, so another way of saying this is the probability of success has to remain consistent. So if you know that in a large population, 48% of people would do a certain thing or would turn out a certain way, or the probability is 4.48, and you keep selecting people from that population, we can assume that 0.48 is going to be a consistent probability of success. But if you do something without sampling without replacement in a small group, then you're likely not going to end up with independent trials. So if you see the phrase with replacement, you can assume that it's independent. You're good. If you see the phrase without replacement, you're probably not going to be independent unless we can ensure a certain condition is met, which we'll talk about in a minute here. Okay. The other thing you need to have is the number of trials fixed in advance. You have to know that I'm going to select 100 people, or I'm going to run this simulation 18 times, or whatever else. You're not counting up to get to 100. You're just going to do 100 and then count the number of successes. So when you know N and P, the number of trials and the probability of success on any trial, if you can show that those two things are fixed and stable, then you have a binomial situation. Okay, I was hearing from folks on the first round of AP exams, they would like describe a scenario and ask you if it was or wasn't binomial. And it seemed like the big thing was that the number of trials wasn't preset. They told you how many successes they wanted, but not how many trials they were going to do to get those successes. So if they ask you, hey, we're going to get 10 successes, they need to set that it's 10 trials, and you're going to count the number of successes in those trials. And so that's what distinguishes binomial from not. We got more stuff in the Cram Hub. We're going to keep it moving. Okay, if something comes up with sampling distributions, they're probably going to ask you to describe a sampling distribution. You do the same thing as anything else: center, spread, shape. Okay, you don't have to talk about outliers because it's probably not going to be a thing. Okay, but this table, okay, these formulas are available to you on the formula chart. Okay, all they're saying, let's look at the second line, center. If you're doing a sampling distribution for a categorical variable and doing p-hats, the center of that distribution is the population proportion. The average of all your sample proportions is the population proportion. The one on the right says the average of sample means is going to be the population mean. Okay, and then those formulas for spread, that's called standard error. Those formulas are called standard error. Okay, standard deviation of a statistic. Notice that sample size is on the bottom. Okay, if you look at the top where it says large counts conditions, you might recognize those numbers: 10 successes, 10 failures for p-hat, 30 for x-bar. Those are the magic numbers to ensure that your sampling distribution is approximately normal. And so when you check the normal condition, if you do inference, this is what you're checking it from. Okay, you're checking that if you're doing a Z procedure, the one on the left, T procedure, the one on the right. We're going to hit that again in a second. But the key here is sample size goes up, your results should become more consistent, standard error goes down. Okay, someone asked about inference. Okay, you need to know one sample Z test or one sample Z interval, two sample Z interval or two sample T test. That's for proportions if you're talking about a categorical variable. If you're talking about a quantitative variable, okay, means one sample T test or interval, two sample T test or interval, or the special case of a match pairs test or interval. No matter what, you've got to make sure that the scenario involves randomness. So random selection can take care of the random condition, or random assignment, if you're doing an experiment, can take care of the random condition. The normal condition is to ensure that the sampling distribution will be approximately normal. So if you're looking at two dot plots and one of the dot plots looks like not perfectly normal, but you've got a lot of individuals on that dot plot, like your sample was bigger than 30, you don't have to worry about the fact that the dot plot doesn't look normal, because your sample is big enough that the sampling distribution, if you repeated this process over and over again, would turn out to be approximately normal. If you've got very small samples for a T test, for a quantitative scenario, you have to ensure that the distribution you're looking at is roughly symmetric. Okay, and then that independence condition is if you're sampling without replacement, okay, you got to show the population is at least 10 times the size of the sample. I will say it doesn't appear that this particular thing is being tested very much this year. It is in the course description, but Questions about conditions that seemed to come up on the first round were mostly surrounding the idea of the sample size being big enough. Okay, that seemed to be the big thing. I have more stuff about inference, but I figure it's going to be better to actually just practice some problems as opposed to me doing this lecture style. So let's just dig into it. Okay, so I've got 2 scenarios set up. Okay, we're gonna go through them. We're gonna practice some answers on the side. We'll talk about what you do and don't need to do to score points, and we'll be done. Okay, so here's our first scenario. Common activity in physical education classes is the running beep test, where students must run a certain distance across the gym and wait for the beep to run back. I'm sure you've all maybe experienced that if you're an American student. The process continues until a student fails to reach the other side, etc. A student in a large high school recruited 50 other students to participate in an experiment to determine if playing motivational music during the beep test would improve performance. The students were randomly assigned to 2 groups. One group completed the beep test with motivational music. The other group completed without anything being played. The groups completed the test at a separate time without seeing the other group compete. The back-to-back stem plot below summarizes the results of the beep test for the 2 groups. Okay, so scenario setup. Okay, common scenario setup is describing some kind of experiment. This is an experiment. And then you're given the results of the experiment. I am curious, before I actually show the sample questions I have, what kinds of things do you think you might get asked to do given this particular setup? You don't have to give a specific, like, we'll be asked to define this exact thing, but like what general kinds of things? So describing, comparing, hypothesis test, like what kinds of things do you think you'll be asked to do? And then I'll show you some sample questions and we'll go through them. I'm also, if you're someone who likes to see things all at once, as opposed to going through the different slides, I have just linked this question with some samples. So yeah, definitely, if you're given graphs, you're probably going to have some kind of setup to compare or describe. Okay, so we can definitely predict that. Angela's talking about doing something about generalization. Yeah, what can we say would be true or not true? So because this scenario involved recruiting people, okay, we didn't randomly pick people from the school. So the results of this experiment can only stay within this experiment. Okay, but we randomly assign people. So if there is a difference, we can say that the music caused it. Okay, so here's 6 scenarios that I came up with for this particular situation. We're going to go through them one by one. So don't worry if you can't read all these. Okay, part A. One student who participated will be selected at random. What is the probability that the selected student completed fewer than 100 reps? And what is the probability that the selected student completed fewer than 100 reps given that they ran without music? Okay, I'll give you about 30 seconds or so to play along at home. You can put answers in the chat if you so choose. And then we'll talk about how to figure this out. Probability from this stem plot that a selected student completed fewer than 100 reps, or the probability they completed fewer than 100 reps given that they ran without music. Okay. Not seeing any answers at the moment, but that's okay because we got to stick to time here. Okay. For this part, okay, probability that you completed fewer than 100 reps. Got to look at the stem plot. Okay. You could be given a dot plot. You could be given a histogram. But either way, you're going to have to do some kind of counting and dividing, some basic things here. Okay. In a case like this, okay, Jeffrey and Angela, your decimals are correct. Okay. Tomorrow, if you're asked for a specific probability, be sure you show where those decimals come from. Most years, showing the fraction is enough to earn credit. So of course you can show the fraction and the decimal, but showing the decimal without showing the setup is not going to count. So the thing I've highlighted is the, in my opinion, bare minimum you'd need to show to get credit. You do not necessarily need to have that notation on the side, but you do need to have the fraction setting things up. Those are the right numbers there. So I'm kind of drawing an imaginary line above 100 and counting. And for the second one where it says, given that they ran without music, I am only going to look at the 25 people who ran without music and counting on that side. Okay, most of you predicted it. Write a few sentences comparing the distribution of reps. So this is where we start making sure that we compare shapes, compare centers, compare spreads. Okay, the good news is in a case like this, if you're comparing, remember that you actually don't have to calculate specifics. You can just speak in general comparisons. So a sentence for center could say something like the median number of reps completed by the group of music with music playing was larger than the median number of reps completed by the group without music playing. I put the medians in parentheses. The median on the left for the with music is 124. The median on the right without music is 101. But you don't have to write those numbers down tomorrow to get credit. Okay, you can just say the median on the left is bigger than the median on the right. Okay, of course, keeping things in context. Notice I'm saying number of reps, group with music. Make sure you're using the scenario in your answer, but you don't need the actual numbers. Okay, I don't see anything with a clear outlier. You could maybe argue that some of the folks with music who finished very few reps could be considered that, but nothing clear and there's no gaps. Okay, the thing that some people might miss on this is both of these graphs to me look skewed to the left. The with music group is skewed left because the way the number line is set up, okay, the tail of that graph is on the low end of the number of reps, not the high end. So if you tilted your head and saw the tail on the right, well, that number line is backwards because you're going from 140s down to 70s. So you have to reorient yourself, skew to the left. If you call the group without music bimodal, I think that would be accepted. Okay, and then the similar sentence for the spread as I had for the center. Okay, the range or the interquartile range or whatever you want to say, but I'm going to go with range because it's easy to calculate. The range with music is larger than the range without music. Okay, part C. In the context of the scenario, explain why randomly assigning the participants to their groups was important. Okay, so we could be asked to explain the rationale behind a component of an experiment. Okay, and if you're doing this, okay, the thing you need to really keep in mind tomorrow is that you have to connect whatever you're talking about to the response variable in the situation. So whatever feature of the survey or the sample or the experiment that they ask you about, you have to ground your answer in how it impacts the response variable. So in this case, the response variable is the number of reps that you complete during the test. So we have to explain why randomly assigning you to your group was important in terms of the number of reps you can complete. So a sample answer could be something like randomization helps create groups of students who are as similar as possible in terms of the number of reps they can complete. This allows for a more fair comparison of the number of reps completed for each group as it helps to balance out possible confounding factors. Someone asked me about confounding earlier. Okay, a confounding variable is what can happen if you do not randomly assign individuals in an experiment. If I had let students choose their group, okay, well, then something else might be going on here because they might choose the group where they feel the most comfortable. And if you choose the group where you feel the most comfortable, your performance is not now dependent on the music. It's dependent on this internal motivation that you have for yourself by choosing the group you're most comfortable with. Or you might choose the group with your friends in it. And now you're distracted or aided by your competitiveness with your friends. And it's no longer the music that's impacting your performance. It's the presence of your friends impacting your performance. So a confounding factor is something that not only impacts which group you choose, but also impacts the response variable. A classic example from a few years ago was there was a scenario about a link between whether or not you smoke and whether or not you develop a certain disease. And there was a link. The people who smoked tended to get the disease at a higher rate. But that was an observational study. No one got assigned to smoke. And so there's possible confounding involved. The people who choose to smoke might have other unhealthy habits like lack of exercise or poor diet. And those factors would probably also influence whether or not you get the disease. And so now it's hard to tell, is it the smoking that's causing us to get the disease or not? Or is it these other things that also impacted whether or not I smoked? Could you say for this question could be reduced? Yes, Jeffrey. So if I determine that the difference between the two groups is significant, that the group with music had significantly better results than the group without music, I could attribute the difference to the music, to the treatments, because the people were randomly assigned. When I randomly assign, I help balance those confounding factors so that the only thing that we're comparing is the treatments. Okay, you could take this a step further and describe like a possible impediment of allowing people to choose their groups, but we were not explicitly asked to do that here. Okay, if you're explicitly asked to describe why confounding may happen, you'll need to pick a variable and go with it. So I picked competitiveness with your friends. So that variable, how competitive you are, yeah, Zane, I think either of these explanations would work. Okay, the key is you're explaining in the first one, the first one's a more generic, like randomization helps balance out the groups to make them equal. And the second one is getting at the idea that randomization helps eliminate possible confounding factors. Okay, if you're going to describe eliminating confounding factors, though, you have to then explain what you're eliminating by doing this randomization. So in the top one, by talking about balancing out and making the groups as similar as possible, you don't necessarily have to like take it much further than that, because that's what randomization does. It helps balance the groups. All right, scenario 1D. Now we're getting into the inference part. So our first three parts, okay, part A came from unit 4, probability. Part B came from unit 1, comparing distributions. And part C came from unit 3, talking about collecting data or why we do certain things in experiments. Okay, the rest of this is all going to come from inference, unit 6 and 7. Okay, student who organized the experiment wants to determine if music would help people similar to those in the study complete more reps on average than those without music. State the name of the test the student should use and write appropriate hypotheses in words for the test. Let's start with choose the test. So you could say 1 sample Z test or 2 sample T test, or I mean, in previous years you would say chi-squared test, but maybe not here. So what test should I use in this situation? And you had a back-to-back stem plot and the scenario. Hope I didn't give it away there. Completing more reps on average with music than without music. Which type of test do you think we should use? Jeffrey says 2 sample t-test. Jeffrey is correct. In this case, we're going to use a 2 sample t-test because when I randomly assigned people to their groups, they are now separate groups. So even though I recruited 50 people at the start, that's one group of people, they're assigned to 2 separate treatments now. Okay. Morgan, great question. Okay, I was about to say that. So match pairs test would be done. Let's say instead of the way we designed it, we designed it so that every person ran the beep test twice, once with music and once without music. If that's the case, then everyone did each treatment, and now both groups contain the same individuals in it, and so now you can pair that data together. Okay, or if I had created little mini groups of like the 2 fastest kids in the class are going to compete against each other, and one of them is going to get music and one of them's not. And the next one, where I have little pairs, that could be paired data as well, where you compare the difference between the fastest and the second fastest and the next and the next and the next and the next. These groups of students were totally separate. So in this case, it's 2 sample instead of match pairs. Z-test, Angela, yes, I will at the end of this kind of give a tour of some of the resources we do have so that you can have a chart to kind of jot down some differences. But the key distinction is Z procedures are for proportions. So the scenario would have to talk about percentage, ratio, rate, or be a categorical variable like yes or no, whereas T procedures are for quantitative variables, means, averages, scenarios involving number of blank. In this case, it was the number of reps. So T procedure for quantitative. Okay. Then when you write your hypotheses, you have to have a null and alternative hypothesis. Okay. This year, because you can type your answers, they're trying to design questions where you don't have to write much notation. So the hypotheses have to be written in words. When you do this, it needs to be clear that a null hypothesis has an equal sign in it, and an alternative has a less than, greater, or not equal sign in it. So notice I've highlighted the word equal to in the null hypothesis and greater than in the alternative hypothesis. The other thing you need to clearly state in your hypotheses is if you're talking about proportions or means. So if you're going to do a Z-test, you need to say proportion of something. And if you're going to say a t-test, you need to say mean of something. Z is for proportion, T is for means. In this case, we're trying to talk about reps on average. So I say the null hypothesis is the mean number of reps completed with music by people similar to the students in the study is equal to the mean number of reps completed without music by people similar to students in the study. Okay, I'm saying similar to those students in the study because that's in the question prompt. Okay, use the information in the scenario to craft your sentences. Okay, it's all going to be there for you. But make sure you say the word proportion or say the word mean, depending on if you're doing a Z-test or t-test. Now we've got a p-value, okay? The appropriate test, in this case 2-sample t-test, yields a p-value of 0.00323. Explain the meaning of this p-value in the context of this scenario, okay? They could ask you to do 2 different things with a p-value. One of them is the thing you're probably super used to, which is the p-value 0.003 is less than 0.05. Therefore, we reject the null hypothesis and conclude that the alternative is, there's evidence for the alternative that the mean number of reps completed by the group with music would be greater than the mean number of reps completed without music. That's not what this is asking. Okay. If you're asked to make a conclusion based on the p-value, you should be doing that reject HO, fail to reject HO, evidence for HA, fail to have evidence for HA. But if you're asked to explain what a p-value is, you're being asked to interpret it. Okay, and in a moment, I will show you a link that has like templates on it for some sample sentences. But for now, just read this answer. A p-value represents a probability when we assume the null hypothesis is true. So a p-value in this case is assuming there is no difference, assuming that the mean number of reps completed by the 2 groups would be equal. So assuming there is no difference in the mean number of reps completed by the 2 groups, the probability that we would observe our sample results is the p-value, and it's as or more extreme than the observed results. Okay, some folks were getting a p-value and asked to make a conclusion, and some folks were getting a p-value and being asked to actually interpret it. Okay, so again, interpreting a p-value is what I did above. Okay, if you're asked what conclusion should you make, or what should you say about the claim, or what evidence do we have, that's when we start interpreting the p-value in terms of, is it greater or less than 0.05? Do I have enough evidence to reject the null hypothesis and go with the alternative? Or do I fail to reject? Okay, and then when you have a p-value, you can potentially have made a mistake. So in this case, the p-value is 0.003. They're asked what type of error may have been made. Okay, remember types of errors. A type 1 error is when we do something by mistake. And a type 2 error is when we don't do something by mistake. So type 1 error is it's like a false positive. A type 2 error is like a false negative. So in this case, what would I have done with this p-value? Well, that p-value is very, very low. So with that p-value, I would have rejected the null hypothesis and concluded that I have evidence for the alternative. So given that that's true, I might have made a type 1 error. since the p-value is very low, we would have rejected the null hypothesis and concluded that music helps people complete more reps. But the mistake would be, there actually is no difference. So there's slides for these scenarios with the explanations. Yes. These slides might not be linked on that hub. I am going to put the link in the bottom of the chat at the very end of this so that you have all the resources there. And I won't sign off until I make sure that everyone can see everything. Okay, because here's the second scenario. Okay, so first one, we did a little bit of comparing data, a little bit of probability, a little bit of why do we do randomization, and then some inference stuff. Okay, you're going to follow a pretty similar structure in the second problem as well. Okay, but what's likely is if the first scenario asked you about means, the second scenario is probably going to ask you about a proportion. Okay, and if the first scenario did hypothesis tests, the second one's probably going to deal with confidence intervals. Okay, it's very likely that they want to get a little bit of everything in there. Obviously, I can't guarantee this, okay, but that seems to be the likelihood. Okay, so here's the second scenario. Dermatologist is interested in verifying the claim of a company that produces acne medication, which claims that its brand name acne cream reduces acne at a significantly higher rate than a generic store brand acne cream. The dermatologist is considering two plans to investigate the claim and wants to focus specifically on teenagers who experience acne. Plan A, from the population of all teenagers with acne, randomly select 200 people, have them use the name brand creamed as directed for a month, and record the proportion in the study who have their acne clear up. Versus Plan B, recruit 200 teenagers with acne and randomly assign 120 of them to use the brand name cream as directed, while the other 80 use the store brand cream as directed. After 1 month, record the proportion in each group who have their acne clear up. If you're given a scenario that has a Plan A, Plan B, okay, you can expect to get asked about each one in some capacity. Okay, so they might not directly ask about each one, but there's probably going to be something about each one. You might have to choose between the two of them for some reason, or you might have to suggest a way to improve upon one of them. Okay, so for example, which plan would be more appropriate for allowing the dermatologist to estimate the proportion of all teenagers with acne who would have their acne clear up by using the brand name cream? Let's just do a quick vote in the poll. Okay, I'm not going to make a poll, just put it in the chat. Just A or B. Based on these two plans, which would be more appropriate for estimating the proportion of all teenagers with acne who would have it clear up by using the brand name cream? Okay, and if all got votes for A. Okay, can someone give just a quick description? What is it about A that makes you pick it for this case? Why would that allow you to estimate the proportion of all teenagers who would have their acne clear up by using the brand name cream? Because in Plan B, I've got people using the brand name cream. It's not just that it's only people using the brand name in A, but Jeffrey's got it. Random selection leads you to make generalizations about the population. Okay, Plan A uses random selection, while Plan B uses volunteers. Okay, so the sample, to take it a little further, the sample of people in Plan A is more likely to be representative of that population than Plan B. Because we're using volunteers in Plan B, there's likely a characteristic about those volunteers that sets them apart from the rest of the population. Perhaps their acne is more severe than the overall population of teenagers with acne, and that's why they want to be a part of this study. Okay, so we want to go further. We want to generalize, we want to use with random selection. Okay, but you'll probably be asked about the other plan. If Plan B were to be altered using a match pairs design with individuals paired together to form groups of two, identify a possible characteristic that could be used to create the pairs, and explain why your characteristic would help the dermatologist answer the research question. So let's just do another quick write. What characteristic about the 200 teenagers could you use to make groups of two in this particular context? What would you use to help make your matched pairs if you're going to do matched pairs? You don't need to then write a full sentence. Okay, Jeffrey's suggesting using gender as a possibility. Any other suggestions before I reveal my suggestion? Jerome suggests age. Okay. So Angela suggests severity of acne. Okay. I dig these ideas. So the thing we got to keep in mind is when you are doing blocking, which is what matched pairs is. So matched pairs in this case is creating small blocks that it's like a stratified sample where you kind of separate the individuals before you do stuff. So if you're going to do blocking or a matched pairs design, you want to ensure that the groups you create are as similar as you can possibly make them in terms of the response variable. So like there's a scenario from a few years back that involved testing different brands of running shoe. And so what we did before designing the experiment was let's rank people by how fast they can already run and then pair up the fastest runner versus the second fastest runner and assign the different types of shoes and have them race. And that will help us tell which shoe is better because we've got, that kind of thing. So Kasheen, the idea of like matched pairs is we're trying to create twins, even if there might not be literal twins. In this case, okay, I see skin type as a suggestion or severity of acne as a suggestion. That feels like a variable that would impact whether or not your acne clears up or how much it clears up. Okay. I agree with severity of acne where you like identify who has the most severe and then the next most severe and so on, because what we're doing is trying to make the groups as similar as possible before we assign stuff. Okay. If I make pairs of one male, one female, one male, one female, one male, one female, okay, that might not have gender might not have as big an impact on whether or not your acne gets cleared up as how much acne you already have having an impact on whether or not your acne gets cleared up. Okay, so I would agree with severity or skin type for this particular case, something like that. But if you're asked why you do blocking or why you do match pairs, it is to create groups that are as similar as possible so that you can make a fair comparison. Going back to the thing about randomization earlier, the reason we do random assignment is to help balance out possible confounding factors because the severity of acne is a possible confounding factor. If I get all the people with really severe cases using the brand name and all the people with the mild cases using the store brand, okay, well, those groups aren't fair to compare against each other. And so now if there is a difference, I don't know if it's really because of the cream or because of what their face already looked like. Okay. In situations like this, you're probably then going to be told about like one plan getting used. So in this scenario, the dermatologist moves forward with plan B as described. So no match pairs. We use plan B, which is all right, 120 of them get assigned to store brand, brand name, 80 get assigned to store brand. Okay. And you're given a two-way table like this. For the 200 people in the study, is whether acne cleared up independent of the type of cream used? Justify your answer without performing an inference procedure. Okay, if you're given a two-way table and asked about something being independent, remember you've got to do the comparison of a overall probability to a conditional probability. So they asked acne cleared up. What percentage of all people had their acne clear up? About 59%. Then I should restrict myself to one of the two groups and see out of that group what percentage of the people had their acne clear up. So let's just go with the brand name right off the bat. Okay. Out of all the people who use the brand name, 61.6% had their acne clear up. Those are close, but they're not the same. And since they're not the same, it's not independent. Okay. They would have to be exactly the same for you to say independent. Even if they're close, can't say it for sure. Okay, if you had done the same thing, but done probability of acne cleared up given store brand, you'd have gotten 0.55. That's not the same either of the 59. Okay, so that could be one way to do it. Okay. 95% confidence interval was constructed from the data above to estimate the difference in proportion for each group who had their acne clear up for the two treatments. The confidence interval brand name minus store brand was calculated to be 0.067 plus or minus 0.139. Based on this confidence interval, what should the dermatologist conclude about the brand name company's claim? Remember, the brand name company's claim was that they're going to be better than the store brand, than the generic brand. So the proportion of people who have it clear up should be higher in the first group than it is in the second group. Meaning, okay, if you're given a confidence interval that involves differences and asked about the differences, there's only one number I need you to care about. And that one number is 0. That is the only number you need to care about if you're given a confidence interval about differences. Okay. If 0 is in your interval, okay, if 0 is in the interval, then that's a problem because it means there might be a difference. If 0 is not in the interval, that's a good thing because then that indicates that there likely is a difference. Okay, the numbers are either all negative or all positive. In this case, okay, Jeffrey, you've got the right logic, but I don't know if you've done the math. Okay, because they've written the confidence interval as 0.067 plus or minus 0.139. So the 0.067 is the difference in the two proportions. That plus or minus 0.139 is the margin of error. That kind of wiggle room to say, all right, the difference in our sample was 6.7%. Okay, the store brand was better in our sample. But if I then look wider, if I construct that margin of error, which they won't ask you to construct, they'll give it to you. Okay, because the test is designed this year so that you don't have to use a calculator. Okay, so they'll give it to you, but you could be asked to do this basic addition subtraction. So if you go ahead and do this addition, you'll end up getting, yeah, if you did, I got you, Jeffrey, you took the margin of error first. Yeah, had it been that way, you would have been right. Okay, but in this case, 0 is in the interval. So when 0 is in the interval, it's plausible that there is no difference, okay? Because think about it, 0 for difference means no difference. If there's no difference, it implies that there's equality between the two proportions. If there's equality between the two proportions, that would be a null hypothesis. So I would just not reject that null hypothesis. Okay, so therefore, the dermatologist cannot verify the claim or does not have evidence that the proportion is higher or whatever you want to say. Okay. Other thing, the final thing we can do here is if the dermatologist constructed a 99% confidence interval instead of a 95% interval, would that change impact our answer? Okay, well, does anybody know what raising the confidence level does to an interval? What does raising the confidence level do to the interval? Does it make the interval get wider? Does it make the interval narrower? Does it keep the interval the same? What does it do? What does raising a confidence level do? Widens it. Okay, so if you're widening it, okay, that would mean that our margin of error was bigger. Okay, well, if the margin of error is bigger, we're still going to have 0, so our answer wouldn't change. Okay, my guess is if they give you a scenario like this, okay, it's probably going to end up being the same answer because, again, they don't want you to make calculations, but they want you to make an argument that, oh, a 99% confidence level would make the interval wider, so the margin of error would be bigger, so the interval would still contain 0. So this doesn't change our answer at all. Okay, and so what I've tried to do is give you a little sampler of different types of questions that have come up. I'm not pretending that this is the only type of thing you can be asked, but okay, if we look at scenario 2, you've got a situation where you have to talk about generalization, something from Unit 3 in Part A, talk about how to pick out a characteristic to make groups. So think of a possible confounding variable and talk about it. You have to do something with independence, that's Unit 4, and then you've got confidence interval stuff. So again, my guess is one of your scenarios tomorrow will involve confidence intervals, and one of your scenarios will involve hypothesis tests, and one of your scenarios will involve quantitative data, and one of your scenarios will involve categorical data. It's also possible that one of your scenarios will involve one group, and one of your scenarios will involve two groups. But I think it's just as likely that both scenarios will involve two groups because there's a lot more they can ask you to do with two groups than just one group. Okay, at this point, okay, I want to remind you about the button at the bottom. Okay, it's a green button that says AP Stats Cram Hub. Hey, y'all, are you still there? My video just went out. Okay, perfect. There we go. Welcome back. So I want to show you and remind you, if you're looking at this screen, okay, this is the, good, we're back. My apologies there. Okay, this has the information from our first cram finale. So there is there's the 5-hour session, but I want to point you out to resources. So if you're looking for, okay, a specific like one pager, okay, the little rocket ship here says stats cram chart. That's got a lot of different templates on it. Okay, so I'm going to open it in a tab, but you're not going to see it yet. So I'm going to have to close this video and then open the other one. Chrome tab, cram chart. Okay, now you should be kind of seeing on the side here. I know it's going to be, I'm not expecting you to be able to read it, okay? But a lot of templates are on here. So I'll specifically point out templates in units 6 and 7, talk about interpreting a p-value, interpreting a confidence level, interpreting a confidence interval, type 1 and type 2 error. Okay, this is definitely a good list of things of just kind of like check, have them there, and you just fill in the blanks. Okay, unit 6 and 7 also has the conditions listed there. Okay, and if you're looking for like, oh wait, someone was asking about like, hey, what are the, like, do you have any lists of how to pick things out? Okay, if you come back to that cram page, okay, with the links on it, okay, I want to highlight that. Yeah, it definitely is super helpful. I can say that for sure. Okay. It was created by a few of our former student interns. Okay, part 1 with Bob, those slides cover units 1 through 4 and have examples and definitions, including like other worked examples. So if you're like, I'm still kind of stuck in random selection, like I need help with stratified samples, that's going to be in the units 1 through 4, so part 1. And if you're stuck on inference, so anything with confidence intervals, anything with hypothesis tests, anything with sampling distributions, part 2 with me is that. Okay, so of course you can still find the 5-hour video replay, okay, but the part 1 and part 2 slides, okay, if you don't want to watch 5 hours of video, I would encourage you to pull up the slides and just click through. Anytime you see a question, try to answer it yourself, and then click again, and it'll animate an answer. So we've got tons of other examples in there with sample answers. And if you're still stuck on how to actually talk about that sample answer, you can then refer to the video and find that spot in the video, and you'll hear us talking through the answers. Okay, so I wanted to make sure you had the access to the cram chart as well as the the resources from the previous ones. I'm also going to make sure I put a link to the replay of the first 5-hour session down here, because it's looking to me like if you click that link at the top that says link to the cram finale, it's going to link you back to this session and not the original session. So give me like 30 seconds here to go find that previous session so that you have access to that as well. Here we go. So make sure this is the right one. You know, I'm getting a little nervous here because the link on the 5-1, oh, link on the top, click more on the top left. Ah, gotcha. Where it says schedule session 2 of 2 and then more session 1 of 2. Okay, thank you, Kashin. That really actually helped me because I was like, why am I seeing the same thing again? Okay, so this is where I'm gonna kind of wrap up in just a moment here, but I want to come off this resource list. Okay, and it's just me here now. So reminders for tomorrow. Okay, 4 p.m. Eastern. Okay, is when the makeup exam starts. Be there half hour early, and be ready to with your paper if you're going to write on paper. If you're going to type, make sure you're ready to type. But trust yourselves. Okay, you have a lot of time, or not a lot of time for either part. I want to say a lot of time. You have not a lot of time for either part. Do what you can, And when there's a few minutes left, just get ready to upload and know that you don't have to answer every question all the way through to still be eligible for credit. In most years, getting more than half of the points available to you gets you a 3. Getting about 60-ish% of the points gets you a 4. And if you can get about 70-ish% of the points, that'll get you a 5. Hard to say what's going to happen this year because of all the changes and it's a much shorter test. It's hard to be representative of a whole year with just 45 minutes. But they're going to do their best to give you a little bit of everything and give you a chance to show your knowledge. So do not sweat if there's one part of one question that you just can't figure out. Okay. Yeah, I'm in agreement about typing. Especially the stats exam, it's looking like you don't need much notation for it at all. So especially if you're a fluent typer, you will be typing answers more than writing, and go with that. So this is where I'm going to wrap it up. Okay, and I'm going to stick around for about 5 minutes or so, maybe 10-ish minutes. And if there's like one topic that you're like, I am super duper extra still stuck on, can you at least show me like the slide that I need to look at? Like I said, this isn't going to be let's reteach the whole course, but if there's a couple of charts or other quick questions you have, I can try to answer those. Otherwise, I wish you guys the best of luck tomorrow. I hope this was a good refresher. And please, please, please use the part 1 resources to help you out and continue to study. Any equation stuff. Oh, this session. Thank you, Zane, for reminding me of that. And I'll make sure that the slide, me doing this right now, actually. The link. All right. Yep. Okay, difference between z-test and t-test. Let me pull up a chart that I've made that can show that. And you'll see in just a moment here. Okay, so the key distinction really comes down to what type of data you have. Okay, so a z procedure, okay, is for categorical variables. Okay, so share screen. Angela, I'll get to your question in a second here. I'm going to talk to Koshin for a moment. Okay, so this is in those slides, the PowerPoint from the original, the first 5-hour stream. Okay, these are the 5 types of tests you need to know, or 5 types of intervals you need to know. You notice categorical variables. It's either 1 sample or 2 sample. There's no match pairs for categorical variables, not a thing. Okay, for quantitative, okay, you're doing 1 sample, 2 sample, or matched pairs. Notice categorical variables, it's Z. Quantitative variables, it's T. Okay, so the questions you need to ask yourself, if you're thinking about what type of test to do, okay, are these. Okay, is your data categorical or quantitative? Are you being presented with bar graphs or two-way table? Or are you being presented with dot plots, histograms, box plots, quantitative stuff? Okay, and then how many groups are there? Okay, 1 group, obviously it's 1 sample. 2 groups, could be a 2 sample, but if it's in the case of a T procedure, we talked earlier, if everyone in the experiment does both treatments and you can pair that data up, that's a matched pairs experiment, or that would be a matched pairs analysis. Okay, but if you have 2 separate groups where the individuals are different in each group, there's no overlap, then it's a 2 sample procedure. Angela, do you mean the answers that we just did, or the confidence interval slides from the first cram finale? Like the one from a couple weeks ago, just to clarify. Or the one from like 10 minutes ago. I just realized both of these are called cram. Okay, I think you mean yes, the old ones. Okay, cool. That's like, all right, so confidence intervals. Okay, so again, I'm not gonna like reteach everything, but the key, so starting at slide 22 of that, Okay. And so just like in those slides as you go through, and again, I would actually encourage you to watch the replay because I'm going to do a much better job there of like walking you through it. But you need to know this formula, the point estimate plus or minus margin of error. Okay, point estimate would be, your p hat or the difference in p hats, or your x bar, your difference in x bars, plus or minus that margin of error. You need to screenshot. Are you talking about the this one? Oh, hey, Harrison. I think she's going to find it somewhere. I'm not 100% sure what you're looking for than that, but yeah, it'll work out. Okay, cool. All right. Well then, cool. Angela, I appreciate that. I was getting a little nervous there. Guys, best of luck tomorrow. Thank you for coming to this session. And again, okay, lots more resources for you to explore. So please, 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 please go through and use it. I shout out to Bob for the first time. He did a great job with units 1 through 4. I like to think I did a pretty good job with units 5 through 7. So definitely take a look at those. And best of luck tomorrow. You guys got this. So yeah, take care. All right. Good night, everyone. Happy studying.